This video lecture is meant to help you see how to do a percent yield problem when you are given lab data, typical of the one you would have seen in the copper silver nitrate lab. So here we have a description of a reaction that says copper reacts with aqueous silver nitrate, AgNO3. After the reaction has stopped, some copper was left over, which means the silver nitrate was used up completely and is considered the limiting reactant. The products of the reaction are aqueous copper 2 nitrate, it's blue, and silver crystals. Here's the balanced equation. So it's a balanced equation. This is a good thing. In our data table, we have a mass of an empty beaker. We have the mass of a beaker and the silver nitrate which at 95.90. So this is the silver nitrate that you started with. And then the third piece of data is the mass of the beaker and the silver crystals. So this was after the reaction, just the silver crystals. We're going to use the data in the data table above to calculate the mass of the silver nitrate used up in the experiment. Okay, so remember, this is the silver nitrate. Okay, we are assuming all of it was used up, but what we're going to need to do is to subtract out the mass of the empty beaker. So this is just a simple subtraction problem, 95.90 grams minus the empty beaker at 93.80 grams to give us a calculated answer of 2.10 grams of AgNO3 used up. Okay. All right, now it says using the answer from part A, calculate the theoretical yield of silver. Remember, theoretical yield, it can be calculated using a three-step stoichiometry problem. And you always start with the limited reactant or the limiting reactant data, which we're told that that's what this number here is. It was all used up, so we consider it the limiting reactant. So we're starting with 2.10 grams of AgNO3. Now what are we trying to find? We're trying to calculate the theoretical yield of silver. That's this right here. So first step, we have to set up a fraction that converts grams of silver nitrates to moles of silver nitrate. So that's the molar mass. 1 mole of AgNO3 works out to 169.9 grams. Of course, that comes from the periodic table. The second conversion fraction is going to use the coefficients from the balanced equation. Since we started with the silver nitrate, we're going to use that coefficient, and we're trying to go to silver, so we're going to use that coefficient. So this works out pretty simply. We're going to have 2 moles over 2 moles. Now keep in mind, it's moles of AgNO3 in the denominator, so it'll cancel with the previous fraction. And we're going to moles of just plain old silver. Third conversion fraction, we're now going to take moles of silver and convert it into grams using the molar mass of silver, which is from the periodic table, 107.9 grams of silver. And when we calculate this all out using the 3 sig figs that we started with, we get 1.33 grams of silver that we theoretically should have been able to make had we used up all 2.10 grams of silver nitrate. Okay. So now we're going to use the data in the data table to calculate the actual yield of silver, right? So this right here is our theoretical yield. The actual yield comes from the data table. So going up to the data table, we should recognize that it is the 94.9 grams. This is the actual yield of the silver crystals, keeping in mind that we're going to have to subtract out that mass of the empty beaker. So I'm going to show my work back in the appropriate spot. And it is 94.95 grams minus the 93.8 grams of the empty beaker. And that works out to 1.15 grams of silver. That's our actual yield. All right, so now we're just doing a simple percent yield problem. So we have 1.15 grams actual yield over 1.33 grams theoretical yield multiplied by 100. We're working with 3 sig figs here, so we end up with 86.5% yield. All right, so there's one more problem that you should work on to get credit for watching this lecture. It's a slightly different reaction, but it works the same strategy. All right, well, good luck, and I'll see you back in the classroom.